Welcome to another video. In this video, we will look at binary search trees. Right? In the previous video, we have looked at various traversals for a binary tree. In this video, we will look at binary search trees. So, what is a binary search tree? A binary search tree is a tree in which all nodes of the left subtree of a particular root node are less than that of the root node, and all nodes of the right subtree of a particular root node are greater than that of a root node. Okay, let us do this with an example. Suppose I have 50, I say here 35, I say here 90. This is a binary search tree because 35 is less than 50, whereas 90 is greater than 50. All nodes to the left of the root node should be less than the root node. All nodes to the right of the root node should be greater than that of the root node. Suppose I say here 25. This is correct. Why? Because 25. So now if I take 35 as a root, 25 is less than 35, and the definition of the binary search tree is all nodes to the left of the root node should be less than the root node. Here 25 is less than 35, and also all nodes to the left of 50 should be less than 50. Therefore 35, 25 both are less than 50. Therefore this is a binary search tree. What if I take this example 85? Is this correct? This is wrong. Why? Because we know that all nodes to the right of the root node should be greater than the root node. Here 85 is greater than this root node, whereas 85 actually is to the left of 50. Therefore here we should have an element where it should be, the element should be greater than 35, right? Whereas greater than 35 and less than 50. Greater than 35 and less than 50. Why greater than 35? Because this node is to the right of 35, and why less than 50? This node is to the left of 50. Therefore, this node should be something like greater than 35 and less than 50. Suppose I say here 40. 40 is right because 40 is greater than 35 and less than 50. Let us look at this example. Now, let us look at the right subtree here. In the right subtree, this element which I am going to insert should be less than 90 because it is to the left of 90, and greater than 50. Why? Because it is to the right of 50, right? So here it should be less than 90 and greater than 50. So suppose I say here 75. 75 is correct. Why? Because 75 is less than 90 and greater than 50, right? So the element which I am going to insert here should be greater than 90 because it is to the right of 90, and greater than 50 because it is to the right of 50, right? So if I say here 110, this is also right. This is also right, right? Now what element should I insert here? What element should I insert here? Right? This element should be greater than 25, right? And should be less than 50. Greater than 25. Why greater than 25? Because I am inserting to the right of 25. Why less than 50? Because this is to the left of 50. Left of 50. So if I say here 38. 38 is correct. Why? Because 38 is to the right. 38 is greater than 25. And 38 is less than 50. Correct? Correct? Okay. I hope that you have understood how to, construct a binary search tree, right? This is just an example. I'll name it as example 1. Example 1. So we have to be very careful how you insert, right? How you insert. Let us look at this example 2. Insertion is in a binary tree. Suppose these elements are given. How do I insert it in a binary as a binary search tree? The first element will become the root node here, 50. Now, next element is 30. Compare 50 with 30, right? Right? 30 is less than 50. Therefore, it should be inserted to the left of 50. Now comes 70. Now compare 70 with 50. 70 is greater than 50. Therefore, it should be inserted to the right of 50. Now comes 20. Now, how do you insert 20? Traverse from the root node. Traverse from the root node. 20 is less than 50, therefore move to the left. 20 is less than 30, move to the left. There is nothing to the left, therefore insert 20. Now comes 40. Now traverse from the root node. The key is to traverse from the root node. Compare 40 with 50. 40 is less than 50, come here. 40 is greater than 30, greater, therefore there is nothing to the right, so insert 40. 40 is done. Now comes 60. Traverse from the root node. 60 is greater than 50, come to the right. 60 is less than 70, insert 60. Now comes 80. Now traverse from the root node. 80 is greater than 50, come to the right. 80 is greater than 70, insert 80. Now comes 35. 35 is less than 50, come here. 35 is greater than 30, come here. 35 is less than 40, insert here. Now comes 45. Traverse from the root node. 45 is less than 50, come here. 45 is greater than 30, come here. Right? 45 is greater than 40, insert here. Now comes 75. 75 is greater than 50, come here. 75 is greater than 70, come here. 75 is less than 80, insert 75 here. This is nothing but insertion. Insertion in a binary search tree. Insertion in a binary search tree. Right? Now, this is the tree which we have already inserted all the elements. Let us look at two more inserts. Let us say 55 I want to insert. What do I do? Compare 55 with the root node 50. 55 is greater than 50, go to the right. Right? 55 is less than 70, go to the left. Now comes 60. 55 is less than 60, therefore insert 55 here. To the left of 60. To the left of 60. Now comes 29. Right? 29 is less than 50, go to the left. 29 is less than 30, go to the left. Right? 29 is greater than 20, insert 29 to the right of 20, to the right of 20, to the right of 20. Correct? So now 29 is to the right of 20 and there is nothing to the left of 20. For the lack of space, I am writing 29 here. Again, I want to repeat, 29 is to the right of 20 and 55 is to the left of 60. Right? This is another example. Now let us look at deletion in a binary search tree. Deletion. We are taking the same example here. Suppose I want to delete a node with 0 child nodes. With 0 child nodes. So what are the nodes with 0 child nodes? 20, 35, 45, 60 and 75 are the nodes with 0 child nodes. So suppose now I want to delete 20. Right? Now I want to delete 20. I can directly delete 20. Right? I can just delete off this element. So I can just delete this element, right? The tree would be the remaining tree. If I want to delete 35, I can directly delete 35. The tree would be the remaining tree. If I want to delete 45, I just delete 45. The tree would be the remaining tree. If I want to delete 60, just delete this. The tree would be the remaining tree. If I want to delete 75, just delete 75. Right? So, if I want to delete all the elements, obviously this would be the remaining tree. But if I just want to delete 20, just 20 would be deleted and the remaining tree would be as it is. Right? So, if you want to delete all the elements, this would be the remaining tree. But if I just want to delete 20, suppose if I just want to delete 20, what would be the remaining tree? So, here would be 50. To avoid confusion, I am just drawing the remaining tree. If I want to delete 20, just delete 20. The other nodes would be as it is. Would be as it is. Right? Would be as it is. 80 and 75. I have just deleted 20. 20 is gone. So this is a very simple way to delete a node with 0 child nodes. So here in deletion in a binary tree, what is a binary tree? First of all, a binary tree is a tree which has either 0, 1 or 2 child nodes, where each node has either 0, 1 or 2 child nodes. Therefore, we can either delete a node with 0 child nodes, we can either delete a node with 1 child node, or we can either delete a node with 2 child nodes. Right? Now let us look at deletion of a node with a single child node. So here in this example, we know that a binary tree is a tree which has either 0, 1 or 2 child nodes. In this example, we have completed deletion of a node with 0 child nodes. Right? In the next example, we will try to complete deletion of a node with a single child node. Here in this, I am taking the same example, that is example 2. I will try to delete a node with a single child. So first of all, let us see what is a node with a single child node, right? Here let us start from the left onwards. Let us start from the left. Now here 70 has 2 child nodes, 30 has 2 child nodes, right? So here 80 has a single child called 75, child node called 75. 80 has a single child node called 75, correct? So here if I want to delete 75, I can just simply delete 75, right? Suppose, okay, if I want to delete 80, so the thing is I want to delete 80, not 75. 75 is a node which has 0 child nodes. So if I want to delete 80 here, I can just delete 80 and 75 will go in place of 80. 75 will go in place of 80 clearly, right? So if I want to delete 75, I will just draw out the node here. There is a correction with my explanation here. I want to delete 80 and not 75. Please make a note of it. 70 here, I will say here 40, 35, 45, 60, and if I want to delete 80, I will move 75 to the place of 80 simply, right? 75, right? And 80 is gone. This is how I delete a node with a single child node. This is how I delete a node with a single child node, right? So here 80 is gone and I will move 75 in the place of 80. I hope you are understanding this, right? So this is how you delete a node with a single child node. Now let us look at the last step. Here we would like to delete a node with two child nodes. Now let us look at one example. Now 50 has two child nodes, that those are 30 and 70. Therefore, what happens if I delete 50? So the first case is, if I want to delete a node with two child nodes, okay, replace that node with the largest element of the left subtree, or replace that node with the smallest element of the right subtree, right? So if I want to delete 50, what would happen? I want to replace 50 with the largest element of the left subtree, So let us look at this. This is subtree of 50. So if I want to delete 50, I need to replace 50 with the largest element in the left subtree. So what is the largest element in the left subtree? 45. Therefore, in place of 50, 45 would come. In place of 50, we will have 45, then 30, then 70. Here I will write 20, here 40, 35, 45, 60. Okay, I don't need to write 45 because I've already replaced 50 with 45, right? So here I will write here 80 and then here 75, right? So if I want to delete, this is case 1, right? This is case 1. If I want to delete a node with two child nodes, I can replace that node with the largest element of the left subtree. Or I can also do another thing. I can replace that node with the smallest element of the right subtree. Both are correct. So here, what is the smallest element of the right subtree? It's 60, right? It's 60. Therefore, I can either replace 50 with 45 or 50 with 60, smallest element of the right subtree. So here I'll replace 50 with 60, then I will draw the tree as it is, right, as it is. So here 20, here 40, here 35 left, and then I will not write I'll 60, I'll just say 80, and then here 75. This is case 1. Case 1 we have seen case 1, and here this is case 2. For case 1, replacing that node with the largest element of the left subtree, and for case 2, replacing that node with the smallest element of the right subtree. This example is for case 1 and this is for case 2, right? Let us look at another example here. So the example I am using here is the same, but let us look at another example where we delete another node. Here in the previous example we deleted 50. We replaced it with the largest element of the left subtree, or we replaced it with the smallest element of the right subtree. Now what happens here, where if I try to delete 30, so 30 is the root node, so I need to replace 30 with the largest element of the left subtree. First case I will replace 30 with the largest element of the left subtree, right? So there is only one element 20, so that is only the largest element, so I'll replace 30 with 20, right? 50 as it is, I will replace 30 with 20, and then the rest of the tree remains the same. Rest of the tree remains exactly the same, right? Okay, this is case 1. Case 2, I will replace 50 with the smallest element of the, so here I want to delete 30, right? So if I want to delete 30, in the first case I replaced it with the largest element of the left subtree. I want to delete 30 now, so here I can also do one thing. I can also, in case 2, I told you I can replace 30 with the smallest element of the right subtree. Smallest element of the right subtree. What is the smallest element of the right subtree, guys? The smallest element of the right subtree is 35. Therefore I just draw like this. So I need to replace 30, right? So I have here 35, and then 20 goes here. I have 40, and then I don't need to draw 35 because I have already replaced it. Then comes 70, then comes 60, 80, and then 75, right? These are the two cases. In the first case, I want to delete 30. So for deleting 30, I replace 30 in the first case with the largest element of the left subtree, which is nothing but 20. In the second case, I want to delete 30. Therefore, I have replaced 30 with the smallest element of the right subtree of 30, that is 35. So here I get this tree, right? So we have seen two cases here, and we have seen actually two examples. In the first example we deleted 50, in the second example we deleted 30. So this is binary search tree, right? We have seen what is a binary search tree. We have seen how to insert nodes in the binary search tree traversing from the root node, and then we have seen how to delete a node in the binary search tree using three cases, right? The first case is a node with 0 child nodes, second case node with a single child node, third case is a node with 2 child nodes. And in the third case we have seen two parts, right? Replacing that node with the largest element in the left subtree, replacing that node with the smallest element in the right subtree. I hope you have understood this lecture. Thank you for watching.